Hello, and welcome back. Today, I want to continue talking about the Class B amplifier by designing, building, and testing such a circuit. I will start off with a set of theoretical calculations, combined with some LT-SPICE simulations, just to verify them, and then I will build and test the circuit in real life. Now, since there's quite a lot to do, this will be a two-part episode. First part being the calculations and simulations bit. So if you're curious, then keep watching. So let's start off with what the circuit will look like, the general schematic, and then start to calculate the components one by one. So I will be building a wideband amplifier with two transistors of the same type, so NPNs, and I will be using a center tap transformer on the output and a one-to-one transformer on the input. This way we can see how both of these types work and what sort of benefits and limitations they bring. So for this design, you don't just need to work on the various resistors, you also need to calculate the transformers. So there's quite a bit to do. So as before, the output will be a 50 ohm termination resistor, and I want to deliver half a watt into it. Now, since we have a transformer on the output with any turns ratio that we want, we can take advantage of this. So we've seen last time that to keep the transistor in linear mode, you're not allowed to saturate it. So there will always be a collector-emitter voltage drop on it, somewhere in the order of 1 to 2 volts. Then, for a bit of negative feedback, we will also be using an emitter resistor, which will also have around 1 to 2 volts of voltage drop at peak collector current. And crucially, these two voltage drops are independent of the supply voltage. So the larger the supply voltage is, the smaller of a percentage these voltage drops represent, so the more efficient the circuit should be. In other words, since we have the transformer, we can design the circuit to work at high voltages and low currents, so high impedances, and then we can simply use the transformer to adapt the output impedance of the amplifier to the impedance of the load. Now, just how high we can set the supply voltage will depend on the actual transistor that we use. We need some sort of low power transistor that has relatively high gain at low currents. So for today's experiments, I've chosen the 2N3904 NPN transistor. So this transistor can support collector-emitter voltages of up to 40 volts, but more importantly, the DC current gain has a peak value at around 10 milliamps. So even lower and higher from this point, we have very good gain values. Also, this transistor has quite a high gain bandwidth product of 300 MHz. So our amplifier's high frequency response will not be limited by the transistor. There will be other things to do that. Now, this particular transistor comes in the TO92 case, which does not have a provision for a heatsink. But for our particular amplifier, we already have two transistors, so any power dissipation will be split up over these two components. So most likely we will not be needing any sort of heatsink, and we will have good thermal performance regardless. Now, since we have an inductor in the collector of the transistor, in theory the maximum collector voltage that we can see is double the supply voltage. So since our transistor can support a maximum of 40 volts, we can set our supply voltage to be 20 volts. Now in practice we will also have the voltage drops on the collector emitter and the emitter resistor, so we will be seeing smaller collector voltages, but we can leave the supply voltage as is just to be on the safe side. Now to get the actual collector voltage, we need to give some values for these voltage drops. So if we set 1.5 volts for the collector emitter voltage and 1.5 volts for the emitter resistor, we get a maximum swing on the collector of 34 volts. And this will be driving 1/2 of the transformer, so the total voltage on the complete primary of the transformer will be double this. So we will be seeing 68 volts. Knowing this peak-to-peak voltage and the peak-to-peak voltage that we need to see on the load, we can now work out the turns ratio of the transformer. So we can split up the primary into two inductors, both having the number of turns P. We have S for the secondary, and just to be on the safe side with the output power, so to make sure that we actually get half a watt this time, rather than trying to supply 14 volts, let's try to supply 15 volts. So knowing that the turns ratio is equal to the voltage ratio, we can work out that the primary has 2.26 times the number of turns of the secondary, so this is one primary half. So the complete primary will have almost 4.5 times the number of turns on the secondary. So now we know the ratio, but this still does not tell us how many turns we need though. So another crucial aspect of transformers design that we need to know is the intended bandwidth. Now I looked at this in more detail another time, so I'll leave some links in the description. But long story short, the transformer's low frequency bandwidth limitation can be calculated based on the output load and the secondary inductance. So if we set ourselves a low frequency limit of 100 kHz, and we also want to get a flat response here, it's a good practice to set our transformer's corner frequency 1 decade below this, so at 10 kHz. So knowing this and the load, now we can work out the secondary inductance value. So this gives us about 795 microhenry. We can take 800 just to make calculations easier. Now, knowing this and knowing the turns ratio, we can now work out what the primary inductance is also. So this gives us 4.09 millihenry for each of the primary side inductors. But this still does not tell us the number of turns that we need. There is one more piece of information that we need. Now, for today's transformer, I will be using an E16 type magnetic core that is made from the FesZ94 magnetic material. Now, according to the product page, this should have an inductance factor of 1.1 microhenry. So knowing this, we should be able to work out how many turns we actually need. But now, if we also check out the material datasheet, so this FesZ94 material, we can see that the magnetic permeability of the material isn't perfectly uniform. So we can't use it at any frequency we want. We can see that after about a megahertz, its real permeability drops off, we get some imaginary permeability. So because of this behavior, the manufacturer specifies this material for transformers up to 300 kHz. So above this frequency, we might be running into certain problems. So when designing an amplifier and choosing a magnetic core, always keep an eye on the actual properties of the magnetic core that you're using. So now, knowing the desired inductances that we want, so 800 microhenry and 4.09 millihenry, and knowing the inductance factor, we can finally work out the turns number for the three inductors. So we will be needing 61 turns for each of the primary inductors and 27 turns for the secondary inductor. So this is the number of turns that our transformer will finally have. Now let's quickly confirm the performance of the transformer, just to make sure that we didn't make any mistakes so far. For that, I prepared an AC spice simulation in which I'm injecting a signal onto one side of the transformer and then measuring what comes out on the other side into the 50 ohm load. So if we use a current source and we look at the output, so we can set a marker in the flat area and another one in a position where we have 3 decibels less. So this is obtained at around 10 kHz as we've calculated. Now, on the other hand, if we perform a voltage simulation with a matching series impedance on the input side, and we look at the output, our -3 decibel point is at 5 kHz, so half of the frequency we've previously measured. But anyway, in both cases, at 100 kHz, we are well in the flat response region of the transformer. So we can go ahead with these inductance values. Moving on, to work out the emitter resistor, we need to know the peak collector current that will be occurring. So this can be determined knowing the secondary side peak current and the turns ratio of the transformer. So we are getting a peak current on the secondary of 141.4 milliamps, which is giving us a peak current on the primary side of 62.6 milliamps. And now, knowing the maximum emitter resistor voltage that we want, 1.5 volts, and the peak current, 62.6, we can work out that we should be using an emitter resistor of 23.96 ohms. Now the closest value that I got is 22 ohms, so that's what I'll be going with. Now moving on with the resistors responsible for setting the bias point, this is where it gets a bit tricky. So the static operating point should be set so that there is almost no collector current, so we can be in class B operation. So we can set ourselves a voltage drop on R1 of 0.7 volts. And under these conditions, we should be getting no or very small collector current. Now, if we have no collector current, we have no base current. And we need this value to set the current running through the bias network. But on the other hand, when we're not in the static operating point, when the amplifier is actually working, we will be getting quite a bit of current. So if the resistors are too large, then the bias point will vary quite substantially with the input signal. So I would be leaving the resistor voltage at 0.7, but as current, I will be taking half of the peak collector current that can run through the circuit. And from there, work out the base current by dividing this by the gain of the transistor. So peak current 62.6 divided by 2 divided by the gain of about 100 for this transistor at relatively low currents, we get a base current of 0.3 milliamps. So now we can set the current running through R2 to be 10 times this, and the current running through R1 to be 9 times this. And now, knowing the currents, knowing the voltage, so R1 0.7, R2 everything remaining up to the supply voltage of 20, we get a set of values for the two resistors. And for R2 I'll be using a 6.8 kilo ohm resistor since this is the closest value that I have. And for R1 I'll be using a 300 ohm variable resistor so that we can adjust the bias point and the operating class. Last thing to work on is this input transformer. So if we take a load resistance of 100 ohms and a target corner frequency of 10 kHz just like before, we get a target inductance of 1.59 millihenry. But with this particular transformer, there are some other things to also consider. Let's look at this in the simulator a bit. So here I prepared a simplified piece of the circuit. So with the input signal source with 50 ohm series impedance, our 1-to-1 transformer, and the 200 ohm loads. Now I'm well aware that the output loads are not matched to the signal source, so the total load is 200 ohms and the signal source has 50 ohms, but that's not our big problem today. So if we run the simulation and look at what comes out the two channels, so first of all we can see that we are getting our flat response at around 100 kHz, our -3 decibel point is somewhere at around 5 kHz, but first of all our amplitudes are different on the two loads, and even more importantly, we have a problem with the phase. So we should be getting 180 degrees of phase shift in between the two. So just to make things a bit easier to compare, if we put a minus in front of one of the channels, this leaves the amplitude the same as it was, but it does add 180 degrees of phase shift to the already existing phase. So what we can see is that we have the proper 180 degrees of phase shift only about 2 decades above our initial corner frequency. So only at very high frequencies do our two signals actually have 180 degrees of phase shift. This is a bit of a problem, since now the two signals that we will be amplifying, being phase shifted when they're recombined, we will have uneven crossover distortion. Now, if we wouldn't have used this sort of transformer, but rather this sort of transformer with an intermediate link to ground, then we would have had none of these problems. So both amplitudes rise and fall at exactly the same rate, and if we add the minus to one of the channels, we can see that we have identical phase on all of them. So even if we don't have a constant amplitude and phase ratio to the input, in between the two signals we have exactly the same thing, exactly 180 degrees phase shifted all the time. But we didn't go with this solution. We went with the other one. So one way to try to fix this without changing the inductance of the inductors is to try to move the corner frequency a bit lower by reducing the load resistors. So if we go with this sort of system where we now have properly matched impedances, so 25 ohms on the secondary sides, we move the corner frequency a bit lower, and we also move the point at which our phases are exactly at 180 degrees a bit lower. So it's not perfect, but we will be going with this for today. Now, for this particular transformer, I will be using the core from an old mains common mode choke. This has quite a large inductance factor, but I do not know that inductance factor. So to figure it out, one method that you can apply is to wind a number of turns, so 43 in my case, and measure the inductance that you get. So I got 6.6 millihenry. From this, you can work out the inductance factor. So now, knowing this and the target inductance that you want, you can work out how many turns you need. So in my case, I will be needing 21 turns. Now, to also get the best possible coupling factor, I will be twisting the two wires of the primary into a single wire, and I will be using this to coil the two inductors at the same time. So this way we should be getting the best possible coupling factor. So this is what the final inductor looks like. Now, before building this thing, let's simulate the complete circuit just to make sure that there were no mistakes made in the process of designing it. So this is the complete circuit. We've got our input supply going through our 1-to-1 transformer. This splits up the signal into two opposing phase signals, which go through the two transistors. So we got our emitter resistors. Now I use two separate ones, but you can use a single one. Then we have the two bias setting networks. The collectors of the transistors go into the output transformer. So this is a center tap transformer with the inductance values that we've calculated. And finally, we have an output 50 ohms. And the entire circuit is supplied from 20 volts. So if we run this thing, so I'm using an input signal with a delay. So just to see the behavior with and without a signal. So if we quickly check one of the transistor collectors, we can see that based on the values of the resistors in the bias network, it has about 760 microamps when there is no signal, and then it jumps up to the full value. So we see peaks of 60 something, 65 milliamps. If we look on the output, just zoom in a bit, we see a nice sine wave, roughly 14.7 volts peak to peak. And we can also check the power that's being delivered. So we have 500 something milliwatts average. So we should be getting the half a watt output using this amplifier. Now, other things to check. So right now I'm running with 300 kilohertz. If we look at the output signal in a bit more detail, so we do see some crossover distortion. It's happening around the 0 volt point. But if we go to lower frequencies, say 50 kilohertz, and we look at the output a bit, we can see the crossover distortion, but this time it's clearly not at the 0 voltage point. So this is coming from the phase shift through the two channels of the amplifier. So we can look at the two signals, and even though they look nice and in opposing phase, if we just take a marker and look over this point where the two cross, we can see that the points where they cross are not always in exactly the same place. So this is a good indication that the two signals are not really in phase. Final thing to look at is the base voltage. And as we can see, even though we've used relatively small resistors, we can see that after the amplifier starts to get the signal, the average voltage drops a bit. So you can see the sine wave slightly dropping. So this is why also on the output we see a bit of a wiggle in the signal. So this could be made better by using smaller resistors, but that would just increase power dissipation. But regardless, this will work just fine. Now I set the input signal to 200 kilohertz. I set the simulation to start saving data after 1.5 milliseconds. And I also added these measurement statements just so we can get an idea of how well the circuit is working. So if we look in the error log, we can see that we are getting a voltage gain of about 2. It's not a lot, but this is what we designed. And we are getting a pretty decent efficiency of 55%. So it's below the 78.5% theoretical value, but it's still a decent value. Finally, we can take the circuit and look at it using an AC simulation. So just to see the response of the circuit over a wider frequency range. And we can see that we are getting a pretty flat response starting from below 100 kilohertz up to above 10-20 megahertz. So this is quite a decent wideband amplifier. So the circuit seems to work just fine. Now, even though this does not seem like a very complicated thing, the Class B amplifier, especially one built with transformers, does require a bit of calculations and fine-tuning to get it to work right. For narrowband circuits, you can of course use some filters on the output to correct any sort of distortions or problems that might appear. But for wideband circuit, you need to take special care with the components and the transformer's design so you don't get any of these problems. For now though, the circuit seems to be fine, in the simulator at least. But the true test lies in real life, and that is the topic for next time. So for now, hope you got some useful information after this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my videos, and see you next time. Bye bye.